Good afternoon, ladies and gentlemen, and thank you very much, Chairman, even though I don't understand anything about Turkish. Thank you very much. I'm Wei LIM from Maastricht University, the Netherlands. I would like to present you the electrical deep brain stimulation of the periaqueductal gray in and defensive behavior. First of all, I would like to give you a general outlines of my talks. I will show you the background and the structure and function of the periaqueductal gray, and followed by our objective and hypothesis. And I'm going to show you two experimental studies here. The first experimental study is devoted to deep brain stimulation of the periaqueductal gray, or PET. And second study is the DBS, followed psychopharmacological intervention with bushburon and escitalopram. And I will tell you more about results and conclusions. Background. Defensive behavior. Defensive behavior is a response of an organism to a potentially dangerous condition in order to protect an organism for survival skill. And it consists of flight, fight, and freeze reaction that accompanied by emotional states such as panic and fearful emotion. In patients, we are often seen as this panic attack. What is panic attack? I assume that most of you are psychiatrists. You know much more better than me. It's an acute moment of intense fear and psychological distress, and followed by these clinical symptoms, which are 13 symptoms in the DSM-4. So these symptoms compose of cardiovascular, neurological, gastrointestinal, and psychological. As you can see, 4 out of these symptoms are able to satisfy the diagnosis of panic attack. How about panic attack in our daily life? Panic attack in our daily life, it can occur in an open space. For example, if you are in the square of the Blue Mosque and then you experience panic attack, as well as it can occur in a closed space or in a dark room. Let's say if you are in the elevator, if you are going to stay at the 7th floor of this hotel, if you feel at this closed space, you have to take the stairs all the way out. So this will cause really social disability, functional disability. Not only that, panic attack can also occur by experimental induce, which we perform with 35% inhalation of carbon dioxide. It's performed in our laboratory in Maastricht. I personally have experienced twice, and it's really induced fear-like behavior, which mimic the panic attack in patient. Furthermore, panic attack can also occur during stressful moments. Like for example, when you have to give a public presentation, or when you are overloaded with a lot of assignments. The current problem, the prevalence of panic attack is about 3 to 6%, which causes severe disability and socio-economic burden to the country. And the underlying mechanism in the brain is unknown. If we go back to 1969, a publication by Nashville, he stimulated the periaqueductal gray for pain reduction. And upon stimulation, he observed intense fear in the patient. And this is probably the first report in our history that stimulation of the periaqueductal gray induced fear-like behavior in 1969. So here, the periaqueductal is located in the deep structure of the brain, and the periaqueductal gray is basically derived from the Greek and Latin word. The peri means surrounding, aqueduct, here will be the aqueduct, and the periaqueductal gray. Because why is called gray? Because this substrate in the brain is like gray-like color, and this structure is connected from the third ventricle to the fourth ventricle. And this is an illustration of the rat brain. Here the horizontal view, and here the coronal view. In coronal view, you will see the periaqueductal gray is composed of 4 longitudinal columns: the dorsal medial, periaqueductal gray, the dorsolateral, the lateral, and the ventrolateral. And we are interested in the dorsal part of the periaqueductal gray. And this is the 3D reconstruction of the periaqueductal gray, as you can see in the 3D dimension. And here I'm going to show you the animation of this structure. In the center of this structure is the aqueduct. So the aqueduct which connects the third ventricle to the fourth ventricle in the brain. It looks like a spaceship or some insects, yeah. So how about the neurochemistry of the periaqueductal gray? The periaqueductal gray mainly composed of the serotonin, dopamine, noradrenaline, glutamate, and GABA receptors, besides and also the neuropeptides and opioid receptors, such as substance P, cholecystokinin, and enkephalin and opioid receptors. How about the physiological function of the periaqueductal gray? If we dated back in 1915 by Brown, he stimulated the periaqueductal gray and then it produced vocalization. And 20 years later, Kaba et al., he performed a deeper stimulation of the periaqueductal gray and is able to modulate the cardiorespiratory function. And recently, way back in 1970 by Richardson, he stimulated the periaqueductal gray for the pain reduction, and he's one of the pioneers in the United States for pain reduction. And sooner in these recent decades by Nobuyuki, Brandau, Blanchard, McNaughton, and periaqueductal gray is mainly involved in defensive behavior, flight, fight, and freeze response. The animal model of panic attack. If we're going to look into the literature, the electrical stimulation of the periaqueductal gray, it evokes a typical behavior which mimics the penny-like behavior characterized by endlessly running and jumping. And this phenomenon is similar to the observation by Nash Ho. I'm going to show you the escape behavior of the rat, in the open field. This is of course a rat. This is a normal behavior of a rat in the open field. This behavior is called exploratory behavior, and the rat is connected with a wire to the stimulator, and then we leave the rat there for approximately 2 minutes for the rat to get used to the open field environment. So once the rat is in the middle of the open field, they will immediately turn back to the wall of the open field, which they feel much more safe. And now I'm going to turn on the stimulation. Once the stimulation is on, and this is what we call the escape behavior. After this escape behavior, or we call it penny-like behavior, the rat remains very fearful and they stay all the time at the corner of the open field. It's just like the agoraphobia. In our first experimental study, we used electrical high-frequency stimulation of the periaqueductal gray to inhibit this penny-like behavior. Before I proceed further, I will explain you what is this high frequency. High frequency stimulation has been used frequently in neurological and neuropsychiatric disorder, for instance the Parkinson's disease, essential tremor, and depression. And what does this high frequency do to the brain? Published by Benazuz in FACET 2004, Meissner in Brain 2005, as well as Wickman and DeLong in Neuron paper 2006. We can come with 3 possibilities of high-frequency stimulation. The possible effect could be the inhibitory effect, which is to inhibit a certain structure of in the brain, or we can stabilization or normalization of the neuronal firing pattern, as well as excitatory effect. You can excite a certain part of the neuron by high-frequency stimulation. So now we came with the hypothesis that with higher frequency stimulation, we will inhibit this structure, that means more than 100 hertz. The normal hertz is about 50 to 60 hertz in the brain. So we are using if more than 100 hertz is considered high frequency. At the same time, we would like to measure this stimulation effect on the animal's behavior and other regional brain activation. First of all, we perform stereotactic surgery. We have the rat placed on the stereotactic frame. Then after that, with the electrode, now we implant on the figure 3, you see the electrode implanted with the cement, and now it's a post-operative period. Our results. Here we have all our rats having the electrode implanted, and this is a histological sections where you see the electrode trajectory, and here's the tip of the electrode. And what do we found here? So on the left column, you can see there's an intensity of stimulation, and the right column, basically we have the low frequency stimulation and high frequency stimulation. In low frequency stimulation, we use 1 to 50 Hertz, and high frequency stimulation 100 to 300 Hertz. In this intensity of stimulation, 0.25 to 74 microampere, we observe the freezing behavior. When we use above the threshold, this above 75 microampere, we observe escape behavior. So in this case, even with high frequency, we are not able to silence or to inhibit this periaqueductal gray structure. And furthermore, we also take into the account of the other regional brain activation. A and B is the control rats or the sham animal, and C and D is the dorsolateral periaqueductal gray stimulated rat. If you can compare the A and C, the control and the stimulated animal, this is a C-force immunohistochemistry. What is C-force immunohistochemistry? This is the immediate early gene marker, which means that if there's a specific activation or neuronal activation in that area of the brain, and you can see a lot of these dotted cells, and these are the dotted cells, which means there is an activation. So M2 is a motor cortex, CG1 is a cingulate cortex. Here you can see there are a lot of activation in the motor cortex. That's why the rat run. And also in the emotional cortex, the CG1, as well as in the prelimbic cortex and infralimbic. IL is the infralimbic. This is a control, not so much of C4 cell. No matter what you see, you will find some C4 cells here, because this is a basal expression of C4s. And here you can see a lot of dotted cells here, which means that these regions are mainly involved in this fear-like behavior, the emotional brain areas. So, the summary of my experiment 1, it was not possible to inhibit this induction of escape behavior with higher frequency. And different amplitudes produce different types of behavior, the freezing and the escape behavior, which are the panic-like behavior. And the pattern of regional brain activation was associated with this intense emotional activation. Now here comes your experimental 2, DBS and psychopharmacological intervention. So in our previous study, as you can see from the video, when we stimulated the rat induced kind of panic-like behavior. And after that, the rat remains all the time at the corner of the open field, which is the fear-like response. So here our hypothesis and objective is to induce these fear-like responses after evoking this escape behavior by DBS approaches. And now we hypothesize that escitalopram, which is the SSRI compound, will reduce this fear-like behavior, but not with bushburon, a classical 5-HT1A receptor agonist, which is only effective for the generalized anxiety disorder, or we call it mild anxiety. Here, I do not have to explain what is this escitalopram, as most of you use it every day. So this is SSRI compound, mainly for the depression, anxiety, and panic disorder. And the bushburon is 5-HT1A, and treatment only for the generalized anxiety, or we call it the mild anxiety. And the chemical structure is non-related to this benzodiazepine. And this bushburon, it does not induce sleepiness in the rat or the drowsiness, unlikely to these benzodiazepines. So our material methods, basically we have two groups of animal, the DBS and the sham group. The sham group, which means the control. In each of these groups, we have the cell line, bushboron and escitalopram treated animals. So all the rats received saline, bushboron and escitalopram treatment respectively. Then here is our results. All these dots, which means that the tips of the electrode, which we perform the electrical the cellular implantation of electrodes, and after our end of the experiment, we had all the brains cut, and this is the trajectory of the electrode. This is the tip of the electrode at the dorsolateral periaqueductal grade. And here is our results. I do not know many of you are familiar with the preclinical works. On the y-axis, you can see the intensity of stimulation, and the x-axis, there are two phases, the escape induction phase 1 and phase 2, which is the acute treatment and chronic treatment. In acute treatment of this drug, it does not change any of this stimulation intensity, whereas after this rat receive chronic treatment with saline, bushboron and escitalopram, and only the bushboron and escitalopram significantly increase the threshold of escape behavior reaction, the intensity of escape within the open field. So only bushboron and escitalopram are effective. And here is the open field testing of the rat by acute treatment. First, I'll give them acute treatment. We would like to compare the effect of acute and chronic treatment. The chronic treatment is after 3 weeks. So here's the acute treatment. The A is the distant move, B is the time in corner in y-axis. What is distant move? Like the less distant move of a rat in the open field, that means they show much more fear. And they move more, which means that they are showing more normal behavior of the rat. As well as the time in corner, we observe that how much time they spend in corner. If they have significantly more time in the corner, which means that they are at the state of fear. If we are going to compare the stimulation with non-stimulation, which is the sham, the stimulated group, they have a significantly reduction of distant move in the open field, as well as significantly increase of time spent in the corner. However, when we give escitalopram treatment is able to reverse back this fear-like behavior, which means indicates that escitalopram might be effective in fear-like behavior, as well as you see in the time spent in the corner, and the rat spend less time in the open field of in the corner of the open field. How about chronic treatment? And this result is similar as compared with the acute treatment. In deepened stimulation of the periaqueductal grade, we observe that there is significantly reduction of distant move and as well as increased time spent in the corner. And when we give escitalopram, they significantly reverse back this behavior. Is the same in acute and chronic treatment. So here comes my summary. Escitalopram treatment is effective for fear-like response in the open field, while bushboron and vehicle-treated rat show no response. Whereas animals treated with bushboron and escitalopram increase the stimulation amplitudes in order to evoke this escape reaction. And in general, my conclusion is electrical stimulation of the periaqueductal grade induces this fear-like behavior or freezing or escape behavior. And high-frequency stimulation was not possible to inhibit this structure, which is accompanied by this behavior, penny-like behavior. And escitalopram treatment was effective in reducing fear-like response generated intrinsically within the periaqueductal grade. And I would like to acknowledge this our department, from the Department of Neurosurgery and Neuroscience, as well as from the Department of Psychiatry. Thank you for your attention.